we know that forces cause extended objects to translate and or rotate. An object that's not extended is a particle. So particles are what we worked with in all the previous videos. We modeled all the objects as particles, so we didn't have to worry about rotational effects of forces acting on those objects. So if our particle is here and it's acted on by some forces, it might end up over here. But since the particle has no dimension, we can forget about its rotation. We can just think of this as a pint. Now, a uniform bar is a simple form of an extended object, and of course, if forces act on it, it could be rotated or translated or both. So let's consider this uniform bar. It's initially at rest. That means that no forces are acting on it. We can forget about the weight of the bar. For simplicity, we can assume that the bar is in outer space, well away from the Earth or any other large mass, so we don't have any gravitational forces acting on it. So we can just imagine that that's the situation. No forces are acting on it. Let's start off with a simple case of forces that act at right angles to the ends of the bar. For simplicity, let's suppose that these two forces have the same magnitude and point vertically up. Now we will follow the usual convention for objects in a plane. Vectors pointing to the right are positive, vectors pointing up are positive. If we follow this convention, we know from the previous video that the sign of the turning effect or moments of these forces will work out. Okay, we'll see now in this example. So how do we characterize the turning effect or rotational effect of forces acting on an extended object? Well, we have to talk about the turning effect of the forces about a particular point. So it depends on the point in question. So we will start with the case where the point is at the center of the bar. So this point is the origin of our coordinate system. Now we are going to get the sum of the moments of the forces about this point. So let's start with this 10 Newton force. We want to get the moment of it about the point C. Now there are two ways that we can do this. The first way is to look at the perpendicular distance of the point C to the line of action of this force. I'm assuming here that the bar is 2 meters long, so the perpendicular distance to the line of action of the force is 1 meter. Okay, this force is at right angles to the end of the bar. So it's very easy to see what that distance is. And what do we do? To get the magnitude of the moment of this force about this point, as we saw in the previous video, we multiply the magnitude of the force, which is 10, by the perpendicular distance, which is 1. So we get 10 times 1, which is 10. Okay, and 10 is the magnitude of the moment of this force. Now, moment is a vector quantity, so how do we get the direction? Okay, is our result positive or negative? There are only two directions to consider. The moment vector itself is perpendicular to the plane of the screen or the page, so we don't actually draw that, of course. We can't see it. Okay, so the 10 Newton force acts to turn the bar clockwise about the point C. And as we saw before, a clockwise moment is negative, so we have to put a minus sign in front of this. So now we have the vector. We don't just have its magnitude. The minus sign indicates the direction. The moment vector would actually point into the plane of the screen at right angles. Okay, if it's negative. If it's positive, it actually points out at right angles. Right, so that's one way we could look at the moment of this force about the point C. Now the other way is to look at the position vector. The tail of the position vector is at the origin, and we draw the position vector perpendicular to the line of action of the force. So straight away we can see that the magnitude of the position vector is 1 meter. But now we have to consider its sign. Okay, it's a vector after all, so for this vector we have to write minus 1 meters. As for the force vector, we can put in the plus sign to indicate the direction of the vector. Okay, it's vertically up, so it's positive. And what we can then do is multiply these two vectors together. So we need to be able to think in these kind of terms also when we're dealing with forces acting on a horizontal object. Okay, so we multiply the position vector, which is minus 1, by the force vector, which is plus 10, and of course we get an answer of minus 10 Newton meters. Now let's get the moment of this force about C. Again, we can think of that in two ways. The first way would be to get the perpendicular distance of C to the line of action of this force, which is 1, multiplied by the magnitude of this force, which is 10. We get an answer of plus 10, which is the magnitude of the moment of this force. And then we need to consider the direction. Well, we can see that this force acts to turn the bar anti-clockwise about this point, and an anti-clockwise moment is positive, so we can just put in the plus sign. So that's one way to do it. The other way is to just multiply these two vectors together. So they're both positive vectors, so we get just plus 1 by plus 10, which is plus 10. Now, so we have the moments of the two forces. We need to sum them, and if we sum them we get 0 Newton meters. So that's not too surprising. The sum of the moments of these two forces about the center of the bar is 0. Now let's consider the resultant force F on the bar. Well, that's very easy to do. We just take the vector sum of these two forces to get plus 20 newtons. So I'll put in the plus sign to indicate that we are talking about a vector, not just the magnitude. Now, what we are going to do is replace the two forces here by the resultant force. The question is, where should we position this resultant force so that it has the same turning effect as the two constituent forces? Now, intuitively, that's very clear. We should position it at the point C. So even without doing any calculation, we can see that it has to go here. Because if we apply a force of 20 newtons at this point on the bar, the bar will not turn. It will just translate upwards in exactly the same way as it would if we applied the two constituent forces of plus 10 newtons to the ends of the bar. We'd have exactly the same movement or motion of the bar. So without doing the calculation we know the answer, but of course in later examples we will have to do a calculation. But let's just see that everything works out. So the principle of moments tells us that we want the sum of the moments of the forces about any particular point, in this case the point C, to equal the moment of the sum or the resultant force about C. So how do we get the moment of this force about the point C? Well, again, I'll use vector multiplication. We multiply the force vector by x, where x is the position vector. And obviously we're going to get 0. We put 20x equal to 0. So here's our position vector. So its tail is at the origin and its head is also at the origin. So it's not even a vector, it's just a point. So this is where we place our 20 Newton force. Now let's take another example. So this time we have an unbalanced, well, the forces in the example before were also unbalanced, but this time this force has twice the magnitude. So what's the turning effect going to be? Well, without doing any calculation, it's pretty clear that the bar is going to rotate anti-clockwise, and it's also going to be translated upwards. So it'll end up here somewhere. But anyway, let's get the turning effect of these forces about the point C. Well, just like before, we multiply plus 10 by minus 1 to get minus 10 for the moment of this force about the point C. Now as for this one here, this time instead of plus 10 we have plus 20. So we have plus 20 by plus 1, which is plus 20. So we get an answer of plus 10 Newton meters. Okay, now let's get the resultant force on the bar. Well, that's simple. Plus 20 plus 10 is plus 30 newtons. Let's get the moment of the resultant force about the point C. Well, we take the resultant force vector plus 30 and multiply by the position vector x, which we will determine. Well, actually, intuitively we can tell that if we want to replace these two forces with the resultant force, we should put the resultant force somewhere to the right of point C. Okay, that makes sense. So let's see exactly where we should put the resultant force. It's not so obvious now. We need to do this calculation. So the principle of moments tells us that we can equate these two statements. So we need to set 30x equal to 10. If we do that, we get x equals plus a third. Now the plus sign is very important. C is the origin of our coordinate system. So we need to position the line of action of the resultant force at plus a third, which is here roughly. Now, an interesting fact about the principle of moments is that when we take the sum of the moments about a pint, the pint can be any pint. Okay, so let's pick a different pint. Instead of C, let's pick this pint here. So let's call this pint A. So this is our new origin, 0, 0. So let's get the moment of the 10 Newton force about the pint A. Well, let's look at the position vector. Well, in this case, the position vector is along the line that's perpendicular to the line of action of the force, along the bar, straight forward here. Its tail is at A and its head is at the line of action of the 10 Newton force. Okay, so it passes through this point. So this is the vector minus 2 meters. Okay, because this point is to the left of the origin. So we have to multiply minus 2, the position vector, by plus 10. So that's going to give us minus 20. Now, what about the moment of this force about the point A? Well, A is on the line of action of this force, so the perpendicular distance of A to this force is 0. So we've plus 20 by 0. Well, that's just 0. So our answer is minus 20 Newton meters. So notice that this answer is different from what we got before. Now let's get the moment of the resultant force about the point A. Well, the resultant force is plus 30. And we have to multiply that by x. X is what we have to determine. It's the position vector of the resultant force. So if we set 30x equal to minus 20, we get x equals minus 2/3. So the minus sign is important here. So we found the position vector of the line of action of the resultant force. So the origin is here. And we go to minus 2/3, which is about here. So notice the interesting fact that the position of the resultant force is the same as before. So this is true in general. It doesn't matter where we take the point that we want to take moments about. It doesn't even have to be on this bar. It could be anywhere. It could be up here. If it's up here, then we have to consider the perpendicular distance of the point to the line of action of the forces. You know, we just have to draw in the line of action of this force and get this perpendicular distance, or well, this vector. This would be our origin 0, 0. So this vector would be negative if our point is here. And if we're talking about the moment of this force about this point, we would have to draw in this vector, which would be positive. Now let's consider a more general example where the position vectors perpendicular to the line of action of these forces are not horizontal. So we won't be talking in terms of position vectors in this example. These three forces are coplanar, of course. That means that they're all in the one plane. We are interested in getting the position of the line of action of the resultant force on the system. Now, I'm not showing any system here. I'm not showing any bar or other object. A is some point in the system. So if the system is a bar, well, A lies on the bar. The system could be a two-dimensional region, you know, some lamina. But what the system is not important. Okay, we can still consider the turning effect of these forces about this point A. So let's get the sum of the moments of the three forces about the point A. Let's start with the 5 Newton force. Well, what do? We multiply its magnitude, which is 5, by the perpendicular distance of A to the line of action of this force, which, as you can see, is 6 meters. So the magnitude of the moment of this force is 5 times 6, 30 Newton meters. Now that's the magnitude, but we want the moment vector. So we need to consider the direction of rotation that this force has about the point A. Well, we can clearly see that it's clockwise, and a clockwise moment is negative. So we need to put a minus sign in here to get the moment vector. So the moment of this force about the point A is minus 30 Newton meters. Now let's take the 2 Newton force. Let's start by getting the magnitude of its moment about the point A. So we need the perpendicular distance of A to the line of action of this force. So we need to draw in the line of action and draw in our perpendicular distance. You can see that it's 7. So we multiply 7 by 2 to get 14 Newton meters. So 14 Newton meters is the magnitude of the moment of this force about A. What about its sign? Well, you can see that the turning effect of this force about the point A is anti-clockwise, which is positive. So we've put in a plus sign here. Finally, let's consider the 3 Newton force. The magnitude of the moment of this force about the point A, as you can see, is 3 times 9, which is 27. Again, you see we have to draw in the line of action, because this perpendicular does not reach this vector. Okay, so it's 27 Newton meters is the magnitude. What's the sign? Well, you can see that this force has a clockwise turning effect about the point A. The clockwise turning effect is negative, so we can put a minus sign in here. Actually, we could have reversed this convention in this question. We could make this minus sign a plus sign, make this plus sign a minus sign, and make this minus sign a plus sign, and it won't affect our answer for the final solution. Anyway, if you put these numbers together, you get minus 43 Newton meters. If we reverse the sign convention, we would have plus 43 Newton meters. Now let's look at the resultant force. Well, let's just see the geometrical construction of the resultant force. So I'm copying this vector and moving it parallel to itself, so its tail is at the head of this 5 Newton vector. Finally, we take the 3 Newton vector and make a copy of this. Okay, so to get the sum of the 3 vectors, I'm going to join the tail of this vector to the head of the last vector that I put here, which is about here. So we're just using the triangle law applied to 3 vectors. So I joined the tail of the first vector to the head of the last vector, and that's the resultant force. Now I've made a copy of the resultant force vector out here. Now, what's its magnitude? Well, we are not going to calculate its magnitude. So you can see that it has roughly the same magnitude as the 3 Newton force. So we'll just say that F is equal to 3 newtons. We just want to understand the method. Now, what about the line of action of this force? Well, here we apply the principle of moments, so I'll just read through the statement of the principle of moments. For coplanar forces, the sum of the moments of the forces about any point or axis is equal to the sum of the moment of the sum or resultant about the point, where the position of the line of action of the resultant force is fixed. So that means that it doesn't matter what point we take. I've taken this point down here, but we could have taken a different point and got the sum of the moments of the 3 forces about this point. We would get a different answer from minus 43. But if we proceed with applying the principle of moments, the line of action of the resultant forces will be the same. So it doesn't actually matter what point we use. So there's nothing special about this point A. I could have used any point. So the sum of the moments about A is equal to the moment of the resultant force F about the point A. So this is also minus 43 Newton meters. The minus sign is very important. So that tells us that F has a clockwise moment about the point A because of the minus sign. So vector F must be up here somewhere, okay, if it's going to have a clockwise moment. You see, if it's down here, it's got an anti-clockwise turning effect about the point A. That's a positive moment. We can't have that. So it's got to be up here somewhere. So now it has a clockwise turning effect about the point A. Now, how do we find the perpendicular distance of the line of action of F from the point A? Well, we will consider the magnitude of the moment of F about the point A. The magnitude of a vector is a positive quantity, of course. So the magnitude is 43 Newton meters. So this is equal to the magnitude of the resultant force, which is 3, times the perpendicular distance of A to the line of action of this force, which we will call D. So now we can find D. 3D is equal to 43, so D is equal to 14 and 1/3 meters. So we need to move this force into such a position that its line of action is 14 1/3 meters from point A. So, well, this is only a rough estimate, of course. Let's say it's about there. Okay, so we want the perpendicular distance of A to the line of action to be 14 1/3 meters from the point A. So this dotted line is the line of action of F. The distance is 14 1/3 meters. So if we multiply 3 by 14 1/3, we get 43 Newton meters, and that's the magnitude of the moment, and we put a minus sign in front of it because it's a clockwise moment about the point A. Clockwise moment is negative. So again, we could have used any point. Like if we had used, say, this point here to take moments about, well, we would have found that our distance d is this distance. Okay, whatever this distance is, and we would have found that the line of action of the resultant force is fixed. It doesn't matter what point we choose to take moments about. By the way, we can place the resultant force anywhere on the line of action. I'm showing it here, but as long as it's lying on the line of action, we can actually place it anywhere for the purposes of calculations. The same is true, of course, for the constituent forces. I could show this 3 Newton force anywhere along this dotted line, and similarly for the 2 Newton and 5 Newton forces.